Alright. So yeah, let's begin. So welcome everyone for the first tea talk of the semester. And today we have Brenda McConer. She is a finishing year graduate student from George Washington University and University of Maryland, College Park. So Brendan, take it away.
Yeah, hi everyone. Thanks for being here and to listen to my talk. I'm graduating in May, and I'll be talking about some of the stuff that's in my dissertation, which mainly has focused on compact objects, both in our galaxy and in galaxies that are far away, and how we identify and follow up these kinds of sources. So I've broken this into three sort of topics that are pretty distinct. The first being galactic X-ray transients and discovery of those with the Swift Deep Galactic Plane Survey using the Swift X-ray telescope. Then I'll talk about my work on the environments of short gamma ray bursts, which are also the environments of binary neutron star mergers and relate to gravitational waves in that sense. Then I will talk about searching for kilonovae from cosmological short GRBs. And I'll start with the sort of galactic science type thing. So first, I would just want to motivate why we undertook a galactic plane survey with Swift. So the main goal is the discovery of new compact objects, such as neutron stars, white dwarfs, black holes. Understanding the galactic population of these sources is a really good way to understand how they formed, how do systems of neutron stars evolve, and that has implications for gravitational waves and a bunch of other types of science, as compact objects, of course, are, we see them all throughout extragalactic astronomy as well, from gamma ray bursts to fast radio bursts, superluminous supernovae. So understanding the galactic population can help us understand how we can perform population synthesis of these other types of systems. So this is also the first sensitive galactic plane survey at these X-ray energies. Past surveys like ASCA were a little bit less sensitive, detecting only the brightest sources. And the past galactic plane survey performed by Swift was a factor of 10 shallower than this survey. So on the left, we see an optical image of our galaxy, and this white box is sort of showing the regions that we're focused on. We also see this on the right, and the red and blue points are magnetars and high mass X-ray binaries alike. So neutron stars, essentially where are neutron stars formed in our galaxy. And we see that our many known systems already form and are known within the survey region. So that motivates looking at these places again with a more sensitive survey, seeing if we can sort of pick some of these out. So on the left is a schematic of our galaxy, and these blue shaded lines are showing our line of sight through our galaxy, right? So we're avoiding the crowded galactic center, which essentially has already been observed by Swift at sensitive searches for it. So we decided to go further away and still, as I said, look in regions where there are many known interesting sources, and we want to find more of them. So in total, there were 380 tiles of 5,000 seconds each, for a total of almost 2 megaseconds. And this is deeper than past surveys. So on the right, we see these tiles all sort of put together in a nice picture. These are essentially the 30 or 40 brightest sources in our survey, all probably above 10 to the minus 11 or centimeters squared per second. So very bright X-ray sources. And we actually find many, many more that you couldn't even pick out with your eye in these images, just because Swift is actually capable of detecting sources that are only a few photons. 5 photons can be a detection in Swift because it has a really low background, especially if those photons are following the PSF. So using our source detection algorithm, we can actually pick out 1,000 sources in those images you were just looking at. And 400 of them were actually not known to any other X-ray survey prior to this undertaking. But we find that only 70 of them are classified. So we have found a number of known magnetars, high mass X-ray binaries, low mass X-ray binaries, CVs. There's also young stellar objects, a couple quasars, and some other types of sources in this other category. But all of these are the brightest sources. They're all like over in this region of flux. So this is a plot of the number of sources versus the flux. And like I said, all the classified sources are over in this region where we only have 150 sources. So out of the 150 sources, which were, found by other surveys, essentially, 70 of those are classified. So our motivation is to classify other sources above this flux level. So we focused on sources that were above 10 to the minus 12 in flux, and we followed them up if they displayed variable behavior. So I'll talk about a couple of those sources that I classified. So on the left is a plot of spin period versus orbital period for high mass X-ray binaries. Those with a BE star companion, a BE star is essentially a massive star, a B-type star that has a decretion disk formed around it, and therefore it shows emission lines in the spectrum, which is why you get the E added to the name. And so we see the spin period and orbital period share a pretty characteristic relation. And in observing IGR-J18219-1347 with NuSTAR and NiSTAR, I was able to confirm the spin period of about 52 seconds. And combining that with the known orbital period of about 72 days, we were able to classify it as a BE X-ray binary. We also did some work on the infrared counterpart showing that it actually is consistent with a B-type BE star. So this was the first object that I worked on. The second was a polar magnetic CV. So polar CV is one in which there's a system with a white dwarf with a very strong magnetic field of about 10 to 100 megagauss. And this is in an orbit with a low mass star or a KRM, late type star, which then matter is funneled from the late type star through the magnetic field lines onto the poles of the CV. And this is why it's called a polar CV. Actually, there's no accretion disk in these systems because the magnetic field is too strong to allow an accretion disk to form. And because of that, these are very distinct objects compared to other typical accretion-based CVs. One of the ways that we know this is a CV, but just looking in this optical spectrum for the Southern African Large Telescope, we see these Balmer lines in blue. They're all of similar height. And this is called a reverse Balmer decrement and is actually a characteristic behavior of these systems. The other characteristic behavior is the He2 line, the helium-2 lines being similar to the H-beta line. And for these properties, among others, based on its X-ray observations, we can classify it as a magnetic CV. So we're demonstrating that we undertook this X-ray survey. We're finding the sources we expected to find, but it's a lot of work to classify every source. There's a number of others that were classified that other people wrote papers on, and a number of other sources that I'm working on as well after these ones are finished. But that's all I'll talk about for the galactic X-ray transient side of things. So I'm going to switch now to short gamma ray bursts, which is another main focus on my work. So short GRBs are caused by the merger of binary neutron stars. We see on the left the famous in-spiral signal from LIGO, and then 1.7 seconds later, there's a short GRB that occurs. A short GRB is defined as being a gamma ray, having a gamma ray duration of less than 2 seconds, okay? As opposed to longer duration gamma ray bursts, which can be higher than 2 seconds and caused by the collapse of massive stars. So the GRB itself, the gamma rays, is produced by a relativistic jet launched in the merger of the compact objects, as we show here. Here's the jet, and here's the merger. And this jet is initially coasting. It's moving through the material around it at essentially the similar speed. After it piles up enough material, the jet will begin to decelerate, and that's when the afterglow starts. So the afterglow is due to this forward shock created by the jet moving through the ISM, essentially. And the afterglow is very important because it emits all across the electromagnetic spectrum and allows us to pinpoint exactly on the sky where these events are coming from. Whereas the gamma rays alone and the gravitational waves are much more poorly localized. So one of the reasons why we care about pinpointing on the sky where these things happen is because we want to identify their host galaxies. But the reason we want to identify their host galaxies is complicated. The first being that we want to understand the distance to these events. What are their redshifts? Short GRBs are much fainter than their long duration counterparts, and they fade very quickly. So it's very difficult to obtain an optical spectrum of a short GRB, and it's actually only been successfully done a few times and actually measured the redshift that way. So in fact, 90% of short GRBs, about 40 or 45 redshifts for short gamma ray bursts, come from a host galaxy association, which can actually be pretty uncertain, and that's one of the things that I'll get into here. But understanding their host galaxy doesn't just give us the redshift, but it also tells us about what type of system formed the gamma ray burst and actually provided indirect support for binary neutron star progenitors well before 170817 occurred. And this is essentially the fact that, one, they were found in both early and late type galaxies. They were found in low and high star forming environments, a low star formation environment being atypical for a massive star progenitor. And they were also being found at large distances from the center of their galaxy, which again is very atypical for a massive star progenitor. And understanding these things informs population synthesis and all of these other important things that we would like to understand in astronomy. But despite all this work, 30% of short GRBs actually lack a host galaxy, even though HST has been used to observe these locations. We refer to these as being hostless. On the right, we see an example of GRB170817 We have a really deep Keck R-band image. Here's the location of the GRB in this magenta circle, but there's nothing underlying it, despite the fact that we have a limit down to 27th magnitude in the optical. This is essentially the best we can do from the ground, and we don't see anything. So we deem it hostless, right? But there's this candidate galaxy really nearby. It's a few arc seconds away, and it's a candidate host. But due to its faintness, it's actually, just possibly a chance alignment. It's not clear that this should be the actual host. When we compute the probability that they're related, we find it's a little bit too high a chance that this is just an unrelated galaxy on the sky. So the important thing to understand for hostless short GRBs is that there is generally always a galaxy nearby that could be the host, but just based on the way we compute these probabilities, it's not clear either which galaxy is the host or that this is the correct one, which in turn can affect our redshift distribution and all of these other things in which we take for granted, but about understanding for GRBs. So that sort of motivates why we study hostless short GRBs. Is one, we want to understand the correct redshift to all these events. We want to understand whether or not this large distance from the candidate galaxy center is real, whether or not the binary neutron star system had this kick happen. The reason kicks are theorized is because when the binary neutron stars form, there's a supernova explosion which ejects some mass, and due to conservation of angular momentum, the system must move in some direction, and that's this kick that we're talking about. This kick can be anywhere between 15 to 400 kilometers per second. It's a really broad range, really broad distribution, and it's not yet well constrained specifically for short GRBs. But the point is that there's this kick, and the binary neutron stars can take billions of years to merge. And after billions of years and some velocity, you can actually move outside of your galaxy. So this is one of the main scenarios for hostless short GRBs. The other possible interpretation is that they're at high redshifts, and we don't detect the host galaxy despite our deep observations. And these two scenarios impact our understanding of natal kicks and time delays in binary neutron stars. If all of them are at large offsets, then they must have long time delays and they must have large natal kicks. Longer time delays means the redshift distribution should peak towards low redshifts, which is going to impact the rate of R-process elements formed from binary neutron stars in the universe. And this is some really important information that we need to start to understand. There's actually been some really nice evidence for a high redshift population lately, which I'll talk about in a few slides, but also I'll mention here. The first being GRB160410A, which is actually, this is the optical spectrum from the Afterglow in the top right from Keck LRIS. This is one of the successful redshifts measured directly from the GRB itself. So we don't have to rely on uncertain host galaxy association here. And this Lyman alpha feature is actually giving us a redshift of about 1.7 for this event. But when we go look in the optical underlying the GRB position, this magenta circle, there's nothing there. And this is a really good case of, we know the direct redshift of this event. We know it occurred within a relatively dense environment because we see this Lyman alpha absorption feature, but we do not see the galaxy. And in fact, there's two other interloping galaxies that we don't see. And this is just motivating the fact that we can miss high redshift galaxies, and we need really deep observations to understand whether or not the GRB is actually hostless or whether we're not seeing the host because it's at a high redshift. So to start to answer this question, I undertook a deep survey of short GRB host galaxies, focusing on those with no host galaxy and no sensitive search for a host galaxy. The motivation, of course, being that 30% of short GRBs lack a host. But this isn't 30% of short GRBs. This is 30% of those with a localization that's good enough that we can say whether or not there is a galaxy. So to explain this, we can look at this pie chart where 35% of short GRBs detected by Swift-BAT have what we would deem a poor localization. This means maybe they weren't detected in X-rays or optical, so that we only have this a few arc-minute gamma ray localization from BAT, in which there's hundreds of galaxies that we could associate to this event, and it's unclear which one would be the host. It would actually be impossible. So we are relying on only those with precise localization, where we can actually say, yes, there's a host galaxy with high probability, or no, we don't see a host galaxy and it's hostless. So starting with this Swift-BAT sample of short GRBs, we applied some selection criteria that the afterglow is well localized, as I said, but also that it's not too near the galactic plane, that the extinction from our galaxy is low enough that our search is still meaningful and isn't just leading us to not find a galaxy because there's extinction involved. So we took late-time optical imaging with the Lowell Discovery Telescope. It's a 4-meter telescope in Arizona, and we observed all of these short GRBs with it. And if we detected a coincident host galaxy to the GRB localization, then we're going to characterize its spectrum either with multicolored imaging to get a photometric redshift, or if it's bright enough, with spectroscopy to get a direct redshift measurement. If we didn't find anything, or we found multiple possible candidates, then we undertook deeper imaging with Gemini, Keck, VLT, GTC, HST, all of these other wide aperture instruments to just go deeper and provide better constraints on this hostless scenario. So the final sample of events that I observed was 31 short GRBs. When we include those in the literature that have already been studied, there are now 72 events satisfying our selection criteria. This is doubling the sample of well-studied short GRBs, and in total, I analyzed about 150 observations in optical and infrared wavelengths across these 31 events, and also about 20 spectroscopic observations to derive redshifts. So one of the main results is that we doubled the sample of XRT localized events. As I said, we need precise localizations on the sky in order to pinpoint the galaxy and in order to measure accurately the distance between the GRB position and the host galaxy center. For X-ray localized events only, they have coarser localizations, about 2 to 4 arc seconds generally. And this is too large to actually say with high certainty what the distance from the GRB to the galaxy is. But we can still associate galaxies to these X-ray localized events, and they still provide important information regarding star formation rates, stellar mass, redshift, and all these other properties that we need to help us understand the progenitors of short GRBs and how binary neutron stars evolve with redshift. So in total, as I said, there's 72 events matching our selection criteria, 52 have a host galaxy, but 20 are still hostless after this deep search, which is 28% of them. And we now need to start to think which one of these scenarios, either large offset or high redshift, is more likely to explain these 20 events. So the first thing we did was look at the luminosity of their galaxies with redshift and how it evolves. So on the right, we see this is an apparent R-band magnitude, extinction corrected versus redshift, and we see it's declining, right? These are the host galaxies of short GRBs. These are redshifts from the galaxy. As I said, only a handful actually have it from spectroscopy of the afterglow. So these are all redshifts based on galaxy association. These black lines are showing us 0.1 to 1 L-star galaxies. So these are essentially how the brightest galaxies in the universe evolve over time, the most massive galaxies. And we see that short GRBs are essentially tracing these really massive galaxies, despite the fact that there are all these gray points are observations of actual galaxies. And we see that there's many that are much fainter, but short GRBs are always tracing the brighter ones until we get out to about these redshifts where there's a few outliers. And the GRB I mentioned before, 160410, is over here. This is an upper limit to its magnitude. And we see that it must be much fainter and is definitely an outlier compared to other short GRBs. And when we look at those with no concrete host association, but with a candidate host, like for 130912a, we take, the one that's most nearby or most probable to be associated with the GRB, but which still the probability that it's just unrelated is a little bit too high to match our selection criteria. That's what these purple diamonds are. And we see that they're all really faint. All of these possible candidate host galaxies are really faint. And when we match them with these black lines, we see that they all have to sort of be above Z of 1. So these are possibly a high redshift sample of short GRBs, which is just not identified based on the way we compute galaxy association. And in fact, when we look at these magnitudes and we say, okay, if we have a 24.5 magnitude galaxy, at what distance from the GRB are we no longer going to be able to say that it's the host galaxy, despite the fact that it might actually be the host galaxy? And we find that to be about 25 to 30 kiloparsecs. So this is possibly a selection biased against a high redshift sample of short GRBs. And that has, interesting implications for their redshift distribution and for the delay time of binary neutron stars. So going to the observed redshift distribution, this is a histogram. In purple, we have spectroscopic redshifts of the galaxy, and blue is photometric redshifts. The median is about 0.5. As we see, there's this nice, really large peak at about 0.5. But recent identification of Z greater than 1 events, not just in this work, but also in recent years, has yielded evidence for a high Z tail, or in fact, a larger missing population of high redshift events. And in this work, I derived 4 spectroscopic redshifts and 8 photometric redshifts at Z greater than 0.5, showing that we can start to populate this tail, and it just takes more telescope time to do it, though. So that's one of the difficulties. So here is a cumulative distribution of their redshifts. In black, this is the sample of short GRBs, and the red and blue lines are essentially models based on a delay time distribution for the time between formation of the binary neutron stars and the merger of the binary neutron stars. So red are models that use a power law distribution, t to the -1 or t to the -1.5, and blue are log normal delay time distributions. These log normal distributions do not predict enough high redshift events. We see there's this large discrepancy here, whereas the red lines actually do predict a similar amount of high redshift events to we find. So we're actually disfavoring log normal models for delay time distributions and saying it's likely a power law. Of course, neither of these two models is perfect, but they do a better job. So one of the games we sort of played was, if all of these galaxies that I showed a few slides ago, the purple diamonds, if all of them are at Z greater than 1, then the median redshift for short gamma bursts is going to shift to about 0.9, which is this dashed line. And what we're saying is that the true redshift distribution is lying between the solid black and dashed black lines. So we're starting to constrain the actual allowed parameter space for short GRB redshifts. But in any case, it's implying that there's a larger population in the early universe, which tells us that binary neutron stars must emerge much faster than we thought. The delay time distribution must be steeper, a steeper power law. And this tells us that binary neutron stars could have been responsible for polluting the early universe with heavy metals, which 10 years ago, based on these blue lines, we would not have thought. So now I'll talk about the offset distribution. This is the projected physical offset in kiloparsecs from the center of the GRB localization to the center of its host galaxy. The black line is the literature, and the red line is this work. And we see they're very similar. Qualitatively, there's not a large difference, and they're consistent with being drawn from the same distribution. So despite the fact that we doubled the sample of events, the offsets are not really changing. The median is still 5 kiloparsecs, and 70% of events are at a distance of less than 10 kiloparsecs from their host. But we do still see that there's this tail of events that are at large distances, likely due to the natal kicks that I was talking about earlier. But the fact that we have a larger sample now means we can sort of start to split things up and look for trends. So when I split these things in redshift on either side of the median redshift for the short GRBs, I found an interesting thing. So the red line are those at high redshifts, and the blue line are those at low redshifts. And what we see is the median offset for those at low redshifts is a factor of 2 larger. And this sort of brings us to question whether or not this is the selection bias I mentioned earlier, where faint galaxies at high redshifts cannot be at a distance of greater than 25 to 30 kiloparsecs, which is this dashed red line here, or whether this is a real evolution of binary neutron star systems with redshift. And it's not clear yet what the truth is. We need to do some more digging for this, and also population synthesis can inform whether or not this is an expected trend, depending on assumptions for natal kicks and time delays, as well as the masses of the galaxies and how they evolve with time. So I'm going to transition again. That's everything on sort of host galaxies. Now I'll talk about kilonovae. So kilonovae are formed following a compact binary merger, either that of 2 neutron stars or a neutron star and a black hole. These mergers eject some neutron-rich material, which then produces, heavy elements through the R process. And as this material begins to decay radioactively, an optical and infrared transient arises, and this is the kilonova. And short GRBs and kilonovae were confirmed to be associated by GW170817 and AT2017 GFO. On the right, we see localization of AT2017 GFO next to its host galaxy, and we see that it's a really red transient. This is about 10 days after the event, and at earlier times, it was much bluer. And now at later times, we're seeing that it's a very red colored source. This blue to red evolution is very typical of kilonovae, and is in fact a signature that we use to identify them in other sources, either in wide field sky surveys or in cosmological short GRBs. So one of the reasons that we're interested in looking at cosmological short GRBs is we expect them to be produced by compact binary mergers, and they're much more common than gravitational wave events or events like 170817 that are just so nearby that they're really bright and can be really easy to identify the kilonova. In fact, short GRBs are detected at a rate of 8 or 9 per year, whereas we haven't detected another kilonovae like 170817 for 5 years. And hopefully we find we find more of them in 04, but that remains to be seen. But the difficulty here is that short GRBs are at much larger distances, and we need really sensitive instruments to be able to place constraints at these distances, which is where HST and James Webb come in. So in fact, HST imaging of GRB200522A revealed a really bright infrared transient about 1 kiloparsec from the center of its galaxy. So here's its galaxy, and here's the localization by these magenta crosshairs. The redshift of the galaxy is about 0.5. And when we do image subtraction between early and late time epochs in the optical and the infrared, we find this transient. And its R minus H colors about 1.3 magnitudes. This is very red for a typical short GRB afterglow. And when we see something red, we think it could be a kilonova. So we have to look in more detail and do some modeling to determine whether or not this could be a kilonova contribution on top of the typical short GRB afterglow. But the fact that we only have one epoch of detection in the optical at about 3.1 and 3.5 days really complicates this for us. So in fact, because we have just one epoch, if we model the GRB with a standard forward shock afterglow in the X-rays, optical, and infrared, we find that including some dust along the sightline, even just a moderate amount of dust, can cause this red color. And this is one possible interpretation for why the transient was very red. The other possible interpretation is that it was a kilonova. And in fact, when we model the afterglow without dust, and then we subtract the afterglow contribution from these data points, we find this sort of remaining flux level. And when compared to kilonova models, we find it matches pretty well with the expectation for large wind ejecta masses. But the fact that we have only one epoch of observation makes it really ambiguous, and even one additional detection would have really favored or disfavored dust for us. So this is an important thing to learn, that we can find kilonova candidates with one detection, and that if there was a kilonova, it would have been detectable by HST at a redshift of 0.5. Future James Webb observations can probably push that threshold up to Z of 1, which would be really nice. But the point is, we need multiple detections, and we need to plan HST programs to observe short GRBs with this in mind, and make sure that we have enough information to disentangle between these two scenarios. But luckily, there are other GRBs that happen, and we get other chances to find kilonovae, which I'll discuss next. So this is GRB211211A. It's a long duration GRB, which I'll show you is due to a compact binary merger. On the left, we see the gamma ray signal of the GRB. It's much longer than 2 seconds, for sure. This is a long GRB, which are typically thought to come from massive stars. And even if we shift this to a redshift of 1, we still see it to be 20 seconds long. So no matter how we look at this event, it's a long GRB. It's not just a redshift effect that that it's just nearby and we see the rest of the signal. This is really strange and very different from a regular short GRB. Here's the field of the GRB, and here's its localization. There's this bright spiral galaxy G1, which we find is at a distance of 346 megaparsecs. And we associate this to the GRB. And there's a few ways we do that. The first thing to mention is we do not have a direct redshift to 211211A from spectroscopy of Afterglow. Spectroscopy at early times was unsuccessful to find absorption features. But what we do have is the fact that it was detected in all UVOT filters by Swift. And this allows us to set an upper limit to the redshift of about Z of 1.5. So we can say it can't be further than Z of 1.5. Now, how do we also favor G1 as the galaxy? First, we've said, okay, there can't be a really high redshift galaxy that we're just missing there. 2, we looked with really deep HST imaging, which is shown here, and we see nothing underlying the position, which would be really strange for a long duration GRB. In fact, when they are at large offsets from their galaxies, typically there's this star-forming pocket that's right underlying the long duration GRB position. So this is another outlier thing here. The other is that we took an optical spectrum of the GRB position and with Gemini, and we set an upper limit to the star formation rate at the actual GRB explosion site of about less than 1 stellar mass per year, which is low for a massive star progenitor and atypical for long GRBs. So the fact that we see a GRB, a long duration GRB, exploding at such a large offset from its galaxy, about 7 kiloparsecs, which is in the 95th percentile for long GRBs, but really typical for a short GRB, as you saw from their offset distribution earlier, allows us to originally favor this as being a really strange event that's possibly consistent with being a binary neutron star merger. But then we look at the light curve, and we find even more evidence that this is atypical. So here we see in black, the dashed line this is the X-rays, and the dashed line is the fit to the afterglow only. The dashed line continues to be the afterglow only, but we see there's this excess in the optical and definitely in the infrared at late times, which is how it was first discovered. And when we model this excess as a kilonova, which is what the solid region and shaded regions are, different kilonova models that can explain this, this is really interesting. We find that this is a kilonova from a long duration GRB in an environment very atypical for long GRBs, favoring a compact binary merger to explain this event. And as I said, when we see red color, it could be dust, right? But the fact that we have this really well-sampled light curve actually allows us to model the SED in time. So the solid line is the afterglow. This is just X-rays and UVOT here. And then we're extrapolating it. And when we continue to extrapolate this afterglow as we move later in time, we see that there's this excess blackbody component as early as 5 hours after the event. And the fact that we see this really nice blue to red evolution, really typical of a kilonova, allows us to say this is not dust. Unlike 2005, 22A, we have conclusive proof that this is a kilonova. And in fact, when we look at the evolution of the bolometric luminosity, temperature of the black body, and radius of the black body, we see it's very similar to the original 2017 kilonova, which is shown by these the gray line and gray points. And we see qualitatively, it's a very similar trend. So this is definitely a kilonova from a long duration GRB, but the main unknown factor right now is actually how a compact merger was capable of producing such a long gamma ray signal. Whether this is the merger of two neutron stars, a neutron star in a black hole, a neutron star in a white dwarf, it's not exactly clear at this point how we can form such a long gamma ray signal. And that's something that'll be very interesting to see in the next few years, how that's shown. So just going to the future and future prospects for detection of these types of events as we move towards 04 in this spring, we computed the rate and we found that about 10% of the electromagnetic counterparts to gravitational waves could be these hybrid or peculiar GRBs. And that would be the best conclusive proof that this is a compact merger producing this event, because that remains to be shown, despite all of this great evidence that it is a compact merger. Gravitational waves would be the smoking gun, the signature that we would need. And if we look on the right, we see detection rate in events per year versus 90% credible area in degrees squared. 03, we didn't see many events, and not many were expected. In 04, it continues to go up. In 05, it continues to go up. And the number of well-localized events is also increasing. So there's hope for more of these events, but 04 and 05 are going to continue pushing gravitational wave event distances further, and detecting kilonova will become difficult for that. So despite the fact that we're having a larger number of events and they're more well-localized, the fact that they're at higher distances also makes it difficult. So let's see if we can get lucky. But I just also want to plug GW170817 and HST, because I think they're really important for solving this high redshift GRB thing. And on the left, we see GRB130912A. This is the image I showed earlier, but I didn't show the HST imaging. So when we look in the optical, we don't see anything. When we look in HST to a similar depth, we see a candidate host galaxy. And the reason for this is because the typical R-H color for a short GRB galaxy is about 2 magnitudes. So in fact, looking in the infrared increases the chances that we're going to detect the galaxy, especially if it's at high redshifts, because there's the Lyman alpha, Balmer break, all these things come into play here. And yeah, so future James Webb observations of these high redshift short GRB candidates will be really good to confirm that. And that would hopefully tell us that binary neutron stars are merging in the early universe, and we'll have to see what we come up with there. So here's my summary slides. So on the Galactic Plane survey sort of things, we detected 1,000 X-ray sources. 40% of them are new. So far, I've classified 2 of them, and more are in preparation. The study of short GRB hosts revealed that 28% of them are hostless still, but that they're likely at high redshifts, and that there is evidence for an evolution in their locations that needs to be explored. And then my work on kilonovae showed that we need multiple epochs and multiple colors to confirm a kilonova in cosmological short GRBs, and that compact mergers can produce really long gamma ray signals, much longer than previously thought. So that's, I'll take any questions.
Yeah, thanks, Brendan, and let's thank Brendan for your talk. Okay, so let's go for a question. Yeah, let's go ahead.
Hi, Brendan. I don't know if you can hear me.
Hi, yes, I can hear you.
Okay, so nice work, first of all. The question I had for you was on your slide where you showed the redshift evolution of the offset distribution.
Yes.
Could you go back to that? So on that slide, the question is, if you relax your constraint of disassociating 25 to 30 kiloparsec as a hard cutoff, right? how much can you push the red line towards the blue? I mean, is it still statistically significant? Because if it is, then it's telling us something really deep about delay times, etc.
Yeah. Yes. So the difficulty there is that these are only ones with spectroscopic redshifts, right? I didn't include those with photometric redshifts or those, of course, without redshifts.
Right.
And the sample that you're talking about that could be at high redshifts, we don't know the exact distance to them. So I didn't include them in this plot. If I do include them, it does push, of course, they're at much larger distances and they're going to populate this tail and make them look more similar. But without actually having spectroscopic redshifts, I would be hesitant to add them. Yeah.
Right. But are they still statistically two different populations, even if you add them? That was my question.
Even if I add them, I don't think I checked when I added them. Yeah, that's a good question.
Okay.
I would have to go back and check my notes.
Because that would be really intriguing if proven, yeah. Right?
Yeah, for sure.
But very nice work over
that. Thank you.
Any other questions from offline or online? Yeah, sure. Go ahead.
Could you talk a little bit more about the mechanism for the longer gamma ray burst in that kilonova that you were discussing at the end? So, like, where does that longer signal come from?
Yes. So at this point, it's not clear how the gamma rays would be produced because we also don't know what type of compact merger it is. That's one of the benefits of gravitational waves moving forward. If we do see a gravitational wave event with a really long gamma ray signal, then we'll likely be able to pick out whether it was two neutron stars or neutron star in a black hole, right? Which would be really important in the first place. But the way we would produce the longer gamma ray signal, as far as I understand it, I mean, simulations will have to show this, but you have to somehow form a really large, so the mechanism for producing the GRB, we would be assuming in this case, there's a merger, and after the merger, there's a black hole remnant, and then there's a disk of matter that accretes onto the black hole, and accretion on the black hole is launching this jet and producing the gamma ray signal. So the gamma ray signal would then be a similar time to the amount it takes for the disk to accrete onto the black hole or the disk to dissipate, right? So the way you can have the longer gamma ray signal is if you can keep the disk around longer, either by changing the viscous radius. So if the disk forms at a larger distance from the black hole, it's going to take longer to accrete, or changing the viscosity, and also the sense that that will affect the time it takes as well. So that's my understanding of how people can sort of play around with current models and produce the gamma ray signal, but I don't think somebody has shown through simulations how to do it yet. And I think the difficulty is that current simulations of mergers and jet launching do not go nearly as long as 50 seconds. A few seconds is even computationally difficult. So that's going to be something that has to be overcome, especially in 3D. In 2D, you can go a little bit longer, but even then it's only maybe to 10 seconds or 20 seconds. It's not out to 50.
Great, thank you.
Yeah.
Yep. Any other questions? Okay. Okay, if not, let's thank Brendan again.
Thank you.
And yeah, thanks a lot for joining remotely, Brendan. So hopefully you will have a chance to visit here in person.
Hopefully.
Yeah, we'll conclude it here. Thanks.
Yeah, and thanks for setting this up so early in your semester or trimester, whatever it is.
Sure, it happens. Okay, bye.